Good morning, friends. Today we discuss a topic on the stern and Gerlach experiment. Okay, so every atom has a spin and orbital motions of electrons. So that is a proof of this concept and also the the spatial quantization of electrons. So these are the two way the stern Gerlach tried to interpret the particular idea in the atoms endowed with magnetic orbital and spin motion of this stage. Okay, so let us discuss in detail about this section. So this is actually atomic magnet of the pole pieces of C and D. Okay, the pole strength PP. This will be the varying of the magnetic field P into P dp by dx L cos theta. Therefore, the atomic magnet is actually the theta should be varied along this particular axis. So therefore the cos theta should be interpreted here. So these are the two poles of this atomic magnet will experience a force, not only a torque and also a translatory force. Okay, so this is a proof of this experiment, proof of this theory. Uh, okay, by using some of the pieces, the copper pieces here, the copper pieces, the copper piece from that pieces. So you have to determine the magnetic moments of orbital and spin motions of electrons. Today agenda is introduction, the stern-Gerlach experiment, theory, experimental verifications, finally the take-home message of the today's talk. Let us discuss in detail. We have seen that orbital and spin motions of electrons in atoms endow with the atoms in the magnetic moments. Of course, இல்லையா ஒரு பர்டிகுலர் ஆட்டத்துல மேக்னெட்டிக் மொமெண்ட்ஸும் ஸ்பின் அண்ட் ஆர்பிட்டல் மோஷன்ஸ் ஆஃப் எலக்ட்ரான்ஸ் வந்து என்ன அட்டாமிக் அதாவது இஸ் மேட் அப் ஆஃப் மேக்னெட்டிக் மொமெண்ட்ஸ். But direct evidence of the magnetic moments of atoms and their spatial quantization is provided by the experiment Stern and Gerlach. So the principle of this experiment is the experiment is based on the behavior of magnetic dipole. This is actually atomic magnet in a non-uniform magnetic field. Before discuss the non-uniform magnetic field, what will happen in the uniform magnetic field applied to the atomic magnet? If the uniform magnetic field the dipole applied to the atomic magnet, the dipole experiences a torque and tends to align the dipole parallel to the field. And the dipole experiences a torque and tends to align the dipole parallel to the field. If the dipole moves in such field, the direction of the normal to the field, it will trace a straight line path without any deviation. This is a situation when you got to apply the magnetic field. In an inhomogeneous magnetic field, the dipole experiences, in addition to the translatory force, if atomic magnet flies normal to the field direction, it will deviate away from the rectilinear path. An expression of deviation produced may be obtained as follows. Okay. Let the magnetic field vary along the x direction, so the field gradient dp by dx is positive. Okay. CD is atomic magnet of pole pair strength P, length L, dipole moment M with its axis inclined at angle theta to the field direction. If the field strength at a pole C is B, then the field strength at the pole D will be P plus dP by dx L cos theta. Hence, the forces of two poles is PP and PP, P, B plus dP by dx L cos theta. Hence, atomic magnet experience not only a torque but also a translatory force Fx equal to dP by dx PL cos theta. This is actually dP by dx mu s cos theta. This is a translatory force will be acting with applying the magnetic field, the non-uniform magnetic field to the atomic magnet. Let V be the velocity of the atomic magnet of mass m enter into the field. V is the velocity of the atomic magnet. L is the length of the atom in the field. T is the time travel to the atom through the field. The time travel to the field is nothing but L by V. This is actually velocity equal to length per time. This is actually T is equal to L by V. The acceleration given the atom along the field direction, the translatory force Fx equal to Fx by m. Okay, Fx by m. The displacement of the atom in the field direction, imagining the field alpha is equal to of at squared of Fx by m into t squared. of fx by m into t squared is nothing but L squared by v squared. Of this is actually fx equal to of dp by dx mu s cos theta by m into L squared by v squared. Mu is represented the component of the magnetic moment, the field direction, mu equal to mu s cos theta. This is such alpha equal to half dp by dx mu by m L squared by v squared. This is actually alpha will be represented the displacement of the atom in the field direction emerging out of the field alpha displacement in the equations. So this is situations of atomic magnet P. We go to the field gradient is increases dp by dx L cos theta. This is actually the CD will be deviated along the particular angle theta with the L. The pole pieces of the two is PP into PP dP by dx L cos theta. Experimental arrangements. Let us verify that concept by using the experimental arrangements. Here just take the silver boiled in an oven. Atoms of silver atoms out opening in the oven. Atoms of silver steams out. அதுல இருந்து ஸ்டீம் ஆகி அதுல இருந்து ஸ்டீம்ஸ் வந்து அவன்ல இருந்து வெளியில வரும் ஹீட் ஆகும்போது by the use of slates S1 and S2 the sharp linear beam of atoms is obtained. அந்த பீம்ல இருந்து ஷார்ப் பீம்ஸை நம்ம எடுக்கலாம். These atoms then pass through the very inhomogeneous magnetic field between the shape of magnet MM. A high degree of non-uniformity in the magnetic field by making one of the pole pieces is produce a powerful electromagnet of knife edge shape and other flat screw cut in opposite direction edge. Opposite to knife edge. எப்பயுமே வந்து பாத்தீங்கன்னா இந்த நைஃப் எட்ஜை நோக்கி வந்து அதிகமான ஃபீல்ட் லைன்ஸ் இருக்கும். The lines of force are close together the knife edge at right angles to the direction of the movement of atoms. Finally, the atoms fall in the photographic plate. The whole arrangement is enclosed in an evacuated chamber. With no field, the beam produces a narrow continuous line on the plate. Clear? The beam produces a narrow beam continuous on the plate. In terms of vector atom model, these atoms with the electron spins directed parallel to the magnetic field will experience a force in one direction, whereas those oppositely directed spins experience a force in opposite direction. According to this, the beam of atoms should split up into two parts. Two parts are split ahum. One approximately equal intensity was actually observed in those experiments. On applying inhomogeneous magnetic field, it was found that say, each silver atom split up into two separate lines. Knowing dp by dx L V mu was calculated, it was found that silver atom had a magnetic moment of one Bohr magneton in the direction of the field. Okay, hence each atom possesses a spin and orbital motions of the particular magnetic moments. Okay, so these are the experimental arrangements. Let us discuss in this oven. The silver atoms is going to be evacuated. The streams of the silver atoms is to be passed through the particular magnet with the collimator S1 and S2. The sharp end is going to be obtained. These are the two non-uniform field is to be obtained. One is a sharp edge, knife edge shaped magnet. Another one is opposite to the crooked shaped magnet is to be placed. This is a non-uniform magnetic field is to be placed. If the non-uniform field is to be produced in this, there will be a high intense lines will be along the particular knife edge is perpendicular to the magnetic field compared to others. So it will have with no field there is a sharp straight line is going to be obtained. If suppose field is to be on, so there is a one field is a spin up and another field is a spin down. So there is a equal intensity of lines of equal width of the path is to be followed through the silver atoms. So if you have to check it up all the L, V and mu values, so each silver atoms have endowed with magnetic moments. Okay. So from these discussions, each atom have the magnetic moments. Each atom is a magnetic moment in terms of orbital and the spin motion of electron, and also the spatial quantization of the particular electrons is also be hence be proved. Thank you very much for your patient listening.